This is the physical science lesson video for section 16.2, and as always, if you want my videos all in one spot, then just subscribe to my channel. So today we're going to talk about ways that heat transfers and the laws of thermodynamics. So conduction is the transfer of thermal energy with no overall transfer in matter. So the energy is moving, but the matter itself is not. Conduction occurs between materials that are touching. And conduction in gases is slower than liquids and solids because the particles of a gas collide less often. So conduction, the two particles must touch. So in a solid, they're really close. Even in a liquid, they're really close. So they'll touch a lot, so conduction can happen quickly. Whereas in a gas, they're all over the place and they touch very little. And so conduction is much slower. But conduction is heat transfer through touch, and of course there's no transfer in matter. In metals, conduction is faster because some electrons are free to move about. So in metals, they have something called the sea of electrons, where the electrons are mobile and can kind of travel between the different metal ions. And so that's why metals heat up very fast. They also have low specific heats, just saying from the previous video. A thermal conductor is a material that conducts thermal energy well. So examples are silver, copper, gold, aluminum, iron, steel, brass, bronze, mercury, graphite, dirty water, or concrete. Okay, notice most of these are metals, and by dirty water I mean it's water with something in it. Pure water itself is not a good conductor. Alright, so maybe just know a couple of these, okay? Just pick a couple of the metals, like ones that would be easy to remember are silver, copper, gold. I mean, those are three pretty easy ones to remember. Whoops, I just clicked the wrong button. Alright, a material that conducts thermal energy poorly is called a thermal insulator. So examples include glass, rubber, oil, asphalt, fiberglass, porcelain, ceramic, quartz, cotton, paper, wood, plastic, air, diamond, and pure water. Okay, so a lot of students, they get confused because they think, well, why can't I swim when it's lightning outside if water is a poor conductor? Well, remember, water you're swimming in, whether it's a pool, whether it's the ocean, whether it's a lake, it's not pure water. In a pool, we have lots of chlorine. In an ocean, you have lots of salt. Okay, it's not pure water, and those added compounds and components make it a good conductor. Alright, so again, maybe just learn a couple of these. You don't necessarily need to know the whole list. So conduction is, of course, heat transfer through touching, and of course no matter is actually transferred. So convection is the transfer of thermal energy when particles of a fluid move from one place to another. So liquids and gases are both fluids. Fluids is anything that can flow. And so liquids and gases are fluids. So convection is the transfer of thermal energy through a fluid moving. So in other words, liquids or gases moving. A convection current occurs when a fluid circulates in a loop as it alternately heats up and cools down. Okay, so like when you're heating water, it's going to be hottest at the bottom, and then that hot liquid is going to rise to the surface, but then because it gets away from the heat, it's going to cool, then so it'll go back down, and that's what's called a convection current. Convection ovens work the same way. Of course, the fluid is air inside an oven. Remember, gases are also fluids, not just liquids. And so it circulates the air, so you have that alternate hot and cold air rotating. That's also the way lava lamps work. When it's near the bottom, it's near the light source, so it heats up, it goes up to the top. But then, because it's away from the heat source, it cools down and it falls back down to the bottom. And so you get that current, that circulation happening. Convection currents are important in many natural cycles, such as ocean currents, weather systems, and movements of hot rock in Earth's interior. So the same currents happen inside of the Earth. Okay, you have the hot, as it kind of goes near the surface, it'll cool down, it'll kind of come back down, so forth and so on. Same thing with the ocean currents between the poles and the equator. Okay, you get that current that goes back and forth. So radiation is the transfer of energy by waves moving through space, and we'll talk more about waves in the next couple of chapters. So all objects radiate energy. As an object's temperature increases, the rate at which it radiates energy increases. So the more energy an object has, the more energy it's going to radiate, and of course the hotter it is. So here's an example of all three. So the fire, of course, is releasing radiant energy into the atmosphere. Alright, here we have convection currents, is that hot and cold water circulating. It's not really cold, all the water is going to be hot, as the hotter versus the cooler water are circulating. And then here, if you touch that hot handle and you feel the heat, then that is conduction, because of course it's through touch. And here's another example. Again, you have the fire and you have that radiant heat, the radiation coming from the fire. You have a convection current of the hot and cold air making the circulation. And then if you touch a hot poker, you can burn yourself because, of course, of the conduction, of you touching the hot surface. So thermodynamics, the study of conversions between thermal energy and other forms of energy, is called thermodynamics. So we're going to learn the 3 laws of thermodynamics. The first law of thermodynamics states that energy is conserved. So we've already talked about law of conservation of energy. Energy can neither be created nor destroyed, or once Einstein came up with E equals mc squared, energy and matter together are conserved. Energy and mass together are conserved. But energy is conserved. So that means, remember, we know it can change into different forms, but the total amount of energy must remain constant in physical and chemical processes. The second law of thermodynamics states that thermal energy can flow from colder to hotter objects, but only if work is done on the system. Another way of saying it is disorder in the universe is always increasing. Okay, so these are kind of 2 different ways of saying the same law. So it's, you can force heat to go from cold to hot if you supply some work. That's how refrigerators work. We force the heat out of the refrigerator when it wants to come in, but we have to plug the refrigerator in. It doesn't just naturally happen. Or, like I said, disorder in the universe is always increasing. And the third law of thermodynamics states that absolute zero cannot be reached. So absolute zero is 0 on the Kelvin scale, and so that is when particles theoretically stop moving, and so we cannot reach absolute zero because we cannot reach to where the particles will stop moving all the way. We can get close, but we're not going to make it all the way there. Alright, and then section assessment. So why is conduction in gases slower than conduction in liquids or solids? Well, remember, conduction is through touch, and gas particles are spread out. So the reason that conduction is slower in gases is because the particles are further apart. Particles are further apart. So number 2, give 3 examples of convection currents that occur in natural cycles. Well, we have the ocean currents, that would be a natural cycle. We have lava under the Earth's surface, it will follow a convection current. We have weather systems, like when you have the hot air masses and the cold air masses. Okay, so we have ocean currents, the lava under the Earth's surface, and weather systems. And then next, what happens to radiation from an object as temperature increases? Well, as temperature increases, the amount of radiation increases. The hotter the object, the more it will radiate. Alright, next one says, state the first law of thermodynamics. Well, first law of thermodynamics is law of conservation of energy. Total amount of energy is conserved in any physical and chemical process. What is the second law of thermodynamics? Well, the second law of thermodynamics, remember, we have 2 ways we can state it. You can say we can force heat to travel from cold to hot if we do work on it, or you can say disorder of the universe is always increasing. Either one is fine. And then next one, state the third law of thermodynamics. Well, the third law states we cannot reach absolute zero, which is 0 on the Kelvin scale, which is when particles stop moving. That should say if your, surprise, surprise, I have a typo if you hadn't noticed, it's in many videos. If your bedroom is cold, you might feel warmer with several thin blankets than one thick one. Explain why. Well, air is an insulator because its particles are far apart, so heat doesn't travel as well through air. So if you have several thin blankets in between each layer, you're going to have a little pocket of air, which is an insulator. And so that air will help keep your body heat within the blanket, making you feel warmer. Whereas if you just have one thick blanket, you don't have those little air pockets to help insulate you. Okay, so you could just say air is an insulator, and so there are air pockets in between each layer, and so that's what helps keep your body heat near you, is because it doesn't want to leave, because it doesn't want to pass through the insulating air. Alright, so hopefully you understand a little bit more about conduction, convection, and radiation, and the 3 laws of thermodynamics.